Good morning. Sorry I'm a bit late. How's the sound? How do I sound right now? I purchased some sound buffers. I don't know what to exactly call them. And I don't think it actually helped my microphone, but you can let me know. All right, so we'll wait for a few more people. How's everybody doing? I was communicating with Omar today. He had a question for me, and we are still communicating. So if Omar, you're there, I will respond to your email after class, okay? What I want to do is pick up with the overview. So I left this for you to look at last week. Okay, Omar, I just have to unravel what you're saying precisely. So I hope you had a chance to look at the probability notes. It's a long unit. Probability, I cover all aspects, preliminary aspects of probability, fundamental aspects of probability. And I like to begin with an overview of relationships, okay, of the probability of events and the probability of relationships of events. And most of you, as I explained last class, have an intuitive sense for this. Some of you studied probability or statistics more recently, and you recall these concepts, but I really want to appeal to your intuition, and I want to correct any misunderstanding or confusion, or I want to correct, not the confusion, but I want to correct your interpretation right off the bat, okay? So as I explained last class, I'm just going to repeat while we're waiting for people. These are complementary events. What is complementary? You can see in the illustration, it means that there are only these events and nothing else. And in other words, they fill the total set of possible outcomes. Knowing the probability of one event then can help you get the probability of the other if there are only two events. You could have, and if there are two events that are complementary, then this is how we solve them. Usually that's what we mean when we say complementary, that there's just two. Okay, and disjoint is allowing for a third option. So there's event A, B, and something else, and I gave a name to the something else relative to A and B. I called it not A or B, very specifically choosing the relational term or. And I also use a symbol that's pretty universal for or union. That symbol is also used, and you might have seen it before. Now when we're looking for the probability of A or B now, we're just focusing on these two events, and I can sum them together because they are disjoint. There's no overlap, and that's why, essentially. There is no intersection, there's no overlap, so repeating the same thing, the consequence is there is no intersection of the two events, so there is no chance of both of them happening at the same time. So you can think of examples for when this is the case. For complementary events, you could say this is the event of it's raining outside, and this is the event no rain outside. It's either one or the other. The example I gave for multiple events, I used the example of a salon, and I said this is a hair color. This is like a manicure. And these are other services that you could get in a salon. So these are all the services you can get in a salon. And in this salon, or the set of salons, you can only get either a hair color or manicure or something else. Then I left you with this exercise, these two exercises, where I mention there are now two events and the possibility that the events overlap. So in terms of the hair salon, you could have a hair color, a manicure, or both, or something else. Okay? So those are the only possibilities here. And then I started to talk about calculating probabilities. I did the same thing up here, and they're pretty standard. I don't even need to know the probabilities to find out the probability of the union, the intersection, which is this, using this symbol here, upside down U, or that's the symbol for intersection. And I know also the probability of not being in either of them if they're complementary. So I didn't even need to know their probabilities. I knew about their relationships. And with disjoint events, given the probabilities, I can solve for the union, but I automatically know the intersection is not possible. And given the union, I can find the probability of the other space. So in this third one, I give you probabilities. You have to be given the probabilities to be able to solve for the union, also the intersection, and the area, there's something else out here. But in addition, you don't just need the probability of A and B, you also need to know what's their intersection. Otherwise, you cannot solve for it. There's no way of knowing what is the probability of their intersection just with the probability. So I'll have to give you this extra piece of information here. And I asked you to solve this. So if you do this, you have to take A plus B, which is like the union of disjoint events, except because they intersect, I double count this intersection piece, so I have to take off one of those. So to do that, I have to be given this value, and then I can calculate 0.3, 0.4 minus 0.1, and the answer is 0.6. Their intersection is already given, so I can just put it here. Oh, sorry. And not A or B would be 1 minus the probability of A or B, which I've already sorted out. That is 0.6, so this answer is 0.4. Okay, so that's how you would have solved that. So again, the important thing is that you're given this value. Now, I explained, before we left, I talked about independent events. Independent look like overlapping events. They must overlap. So independent is not disjoint. Those are different concepts. Independent is where that says occurred. Let me fix that. So knowing that one occurred does not affect or change the probability of the other occurring. So I explained that. Let's say you were here, so you know someone in the salon with this characteristic, with 30% chance of having hair colored and 40% chance of having a manicure. This is all unit 4. So if you knew this and you were here, so you see someone has their hair color, the question is, what is the chance that they also have a manicure? If they're independent, it means the chance of being here is 40%. And the chance of being here is also 40%. The probability of the event B doesn't change if you're in A or in all of S. It's still the 40%. How does that affect things? Well, when I want to figure out probability of A and B, let me say and, because I've been using the words. To find the probability of A and B in general, what you have to do is you need to know the probability of A, and then of those events, or within A, what's the probability of seeing B given A? This is actually how you would calculate the intersection if you didn't have it. Okay, so this is important. This is a formula or definition. So this is how I would calculate A and B. I need to know the probability of A, and I'd multiply it by the probability of B given A. And I just multiply those together. So that's in general. This means given. So it's saying you're in A, what's the chance of B? So it's saying of the times I'm in A, what's the chance of being in B? Or anyway, I multiply them. The multiplication tells me is from saying of. So do I know these probabilities? Well, I know A, that's known. But do I know B given A? So that's my question. Do I know B given A? We're on Unit 4, Edwin. We're on Unit 4, probability. This is page 7. Exactly. So what happens, so Manuel's right, very good. So because I told you they're independent, then probability of B given A doesn't change from probability of B. Those are the same thing. Oh, let me write that. So the answer is yes, since A and B are independent, probability of B given A is just probability of B. It doesn't change. So this is also 40%. As a result, the probability of A and B is just probability of A times the probability of B, which is equal to 0.3 times 0.4, or 0.12. Now that I have that, I can calculate the others. All right. So what about A or B? Let's calculate that. To make a little space. So A or B would be probability of A plus probability of B minus the overlapping piece that I now know what that is. So that's A plus B minus 0.12, which is 58%. Very good, Angel Anibal, yes. So I have this result is 0.58. This one is 0.12, and then not A or B is simply 1 minus probability of A or B. 1 minus 0.58. And that's it. Those are the probabilities, okay? So, some things to wrap up. What's been said, when the events are overlapping, they look like events that are independent in that they have an overlapping piece. So overlapping is not going to give you the probability of one and the other. I'd have to be given that information or have extra information to be able to calculate it. If they're independent, the probability of the event given the other one doesn't change. So I'm just multiplying using the B. Now, before I go on, I want to also stress that I could have written it differently. I could have said, so that's what I wrote above, but also I could have written it like this, because essentially this breaks down to being the same thing. Because of independence, the probability of B of given A is just B. It doesn't matter that A happened. It doesn't change the probability of seeing B. And similarly, if I did it this way, if B happens, it doesn't change the probability of seeing A. And so these are the same. So I could have written it either way. So one last thing I want you to see or notice about this is known as the conditional probability. So conditional probability, because of this property that I've demonstrated, or the definition of conditional probability, it comes out of thinking of the intersection. So if I did some algebra, isn't this the same as no, like when that happens. Let me So I could write this, because I can take and isolate this, right? And divide the intersection by probability of A. I can do the same for this amount and divide A and B by probability of B. So these are the conditional probabilities. What is it saying? It's saying to rescale the chance of seeing A and B by the chance of seeing A. So it's like saying rescale to this event. So you can see A on this drawing, you can see A and B on this drawing, but the conditional probability, you don't see it in the sketch. I mean, it's not exactly intuitive to see that, and that's probably why people get confused. Okay, so you see A and B, but the conditional is saying being in here as a fraction of being here. So it's rescaling the drawing just looking at the event A. All right, any questions about conditional probabilities? So you've learned about events, their relationships, and I've introduced the concept of conditional probability, which the rest was fairly intuitive. Maybe this wasn't. So this is probably all you really have to study, okay? Understanding what's going on here, rescaling, or It's like standardizing it by, okay, it was rescaling it. All right, so if you don't have any comments, I'm going to move to looking at the overview of this unit. Well, to review the unit, because this was the overview, the main concepts. Remember to refresh your screen if it looks blurry. Any comments? Looks a little blurry. Okay, let's see. So I'm going to go to the beginning. Okay, so what's the purpose of all of this? Just going to all right, so our objective is to learn about the theory behind estimation and then to use it, the theory, to compute estimates and to make inference about the population. Inference means educated guessing, okay, or informed guessing of estimates. In particular, parameters, sorry. In particular, we are going to learn about the relationship between statistics of samples drawn from a population and the parameters of the population themselves, or itself. We will take what we learned to make conclusions given two types of questions. First, we're going to determine the value of statistics given information on the parameters. Okay, that's what we're going to do with this probability theory. And then we're going to do the reverse. Determine the value of the unknown parameters given the value of statistics. So as I mentioned last time, we're going to build this bridge from parameters to statistics and then knowing parameters, what are the statistics? Now that's not as interesting, but it is a skill, and it does derive, our theory derives, well, we developed the theory to do this, but what purpose it has is really to go from samples where we have statistics and we want to know about the parameters that are unknown. In the first instance, We know parameters, we can calculate statistics, what to expect in samples. We can predict what to expect in samples. On the other hand, what's more interesting is given samples that you can go collect and unknown parameters, we can use the same theory to find out what are possible, the values of parameters that are really unknown. Okay? So, some events in the world are purely deterministic. That is, they have a known outcome. For example, my car will not run without gas. It's 100% true, right? It's deterministic. Some events are random, however. For example, when you flip a coin, you know that either a head or a tail will appear, but you don't know which one will appear on any given flip. So if I asked you what's the chance of seeing a head on the flip of a coin, you know this is 50%. But what does that mean? So I'll give you an illustration. It's possible, because of randomness, it's possible that someone, so let's say this was a junior to you, either a nephew or a younger, or a child, or a young person, decides to start flipping a coin. You know, children have a lot of time on their hands. So they decide to flip a coin, and they flip a coin looking for heads. And it turns out that the coin was flipped times, and a head was not seen even once. So this says 50 times. I'll say 50 flips. How do you reconcile what we know about probabilities intuitively and this outcome? How do I reconcile that this youngster had flipped a coin 50 times and never saw a head? Out of 50 flips, doesn't that mean 0% chance of a head? So how do you reconcile that it should be 50%? How would you respond to this instance or to this youth? Any comments? Yeah, that's what it looks like. It looks like the chance of a head was 0 and the chance of a tail was 1, right? Omar. So what do you say in this instance? It's really important, so I'm going to give you some time to think about it. Okay, yes, they are disjoint events. That's true. But that wasn't answering my question. But they are disjoint events, right? Very good. Either it's head or tail. They're also complementary events, right? Because it's either head or tail, and that's it. So how do we reconcile that we didn't get 50% out of all those chances, all those flips? There's nothing wrong with the coin. It's just possible. It is possible that this could happen. No idea? So if you have no idea, write in the chat that you have no idea, so at least I know you're listening. And you understand the question. So how do you reconcile that this person flipped 50 times and had not seen a head even once? No comments? Are you guys watching? Well, it's better if you tell me than I tell you, but okay, let's see. The issue is that, or what you should tell this person is go back and flip some more, because you haven't observed the long run relative frequency. This is a relative frequency, right? So you see 0 out of 50. This is a probability. It's a relative frequency. But you haven't flipped enough to see the long run effect. Thanks, Paula. So this is the issue. Probability is long run relative frequency. And your answer, simple answer, is keep going. Eventually, if you flip enough times, and enough depends from event to event, how much is the long run or what is the long run, it turns out. So this is doing this experiment, right, where I'm flipping coins. So this person flipped just once, and they had a head, so that's 100%. And then you see flipping 3 times, 5 times, the proportion was like 0.7, I guess, for 5 flips or 6 flips. Anyway, this is not a scale drawing, but they just to fit it into this textbook, they made it look like this. So it looks like it takes about, more than 100 flips before you see that the proportion of all the flips is 50% heads. You see, it converges to 50%. You follow this diagram? So what we did was we did 50, right? So the kid did 50, actually ended up here, 50 flips was 100. So it was, it would have just been a line like this, which is very unlikely, but it's possible. This is just one experiment. and the sample size was changed every time, like the number of flips would be your sample. And it takes about more than 100 flips, so over 200 flips to see that it converges. And even then, it's not exactly 50%. So for this experiment, this is what happened. It would probably be better to do this experiment many times and use the average, and you might see it flatter. But if you take this one experiment, you just vary the number of flips, and you keep calculating the ratio of heads over total flips, this is one possible graph. Okay, so from there, converges to not 0, 50%. This is 50%, Edwin. Okay. So you can read about what I've had to say here, but what probability is? Probability is long run relative frequency. So there's some randomness and uncertainty until you see the regularity of the pattern. Questions? Paolo, I don't know what you mean about the box, but you have to flip it enough times. If it's a coin, you have to repeat the event, the phenomena, enough times to see its behavior, or its long run behavior. So you're talking about like a dice? Oh, but a box that doesn't have 6 sides? Yeah, Pablo. Oh, it's Pablo, not Paula. Yeah, so 2 sides on a coin, and if you did a dice, it's 6 sides, the same sort of thing. Yes. So if you used a dice, it would be the same thing. So a dice, number 1 has 1/6 chance. Number 2 has 1/6 chance, right? Every number up to 6 has a 1/6 chance. And you'd have to roll that dice enough times to see that behavior exactly. All right, so this is the same if any of you gamble or you know about gambling. When they have in gambling, another example would be the roulette table. Well, there's all kinds of examples in gambling for probabilities. So if you think of the roulette table, and I'm not an expert, but essentially the thing I want to talk about is I know that behind the table, sometimes some casinos, they have a screen or that posts the last outcome, whether it was a black, what number it was. Some casinos actually show the last rolls. So this gives players some sense, that they can predict what's going to happen next. But in fact, the probabilities, because the casino, the house, plays so many times, right? They're operating with long-run relative frequency. But an individual player standing there is just looking at the board thinking that they have some sort of control. But in fact, the roulette wheel, I think there's 36 spots. Each has a 1 in 36 chance, and a black has half the chance as a red. So those probabilities are independent. They don't change from time to time. And the fact is the house operates because it flips so many times, or it spins so many times, or it rolls dice so many times. It's operating with long-run relative frequencies. But you don't stay there as a casino player. You're not there as much as the house is there. So yours is much more volatile, your situation. You can't make predictions very well. Okay, so you're subject to the uncertainty of the short run, whereas the house is operating with the long run and more capable of making predictions. So I don't gamble. I never have gambled. I rarely buy a lottery ticket because the odds are against me. However, having said that, I will tell you, it's not exactly a secret, but I will tell you that my parents did win a lottery when I was a kid, but they never told me and my siblings. They did win a lottery. They didn't want us to think, it's so easy. They didn't want us to be addicts because we actually had an uncle who had problem gambling. But yeah, that's what happened. My parents split $1 million with a group of 10 people in the 70s. So it can happen, it could be up here, but it's a chance event. So what I'm trying to do is differentiate for you the short run, and the long run. All right, let's see. Oh, you guys couldn't see what I was writing? Okay. I have to be careful. I shrank the... I wrote change here. It should be chance. Any questions? All right, so some other comments I made in these notes. And this is to refine your understanding of probability, of chance, okay? That's why I want to spend this time to discuss it. Regarding independent events, two compound events, A and B, are independent. I'm talking about events A and B. So when I say compound, what I mean is that the event A can be made up of all these sub-events. And so event A and B are independent if knowing that the outcome A occurs does not influence the probability that B occurs. So it doesn't change the probability distribution of the events in B. It doesn't change the chance of B and happening or any of the events that are included in B. Similarly, if you think about in terms of trials, a trial is independent if the outcome of one trial does not influence the outcome of any other. So that would be in sequential events. So like flipping a coin, from flip to flip, the probability doesn't change. All right. What about when people talk about, and I'm going to spend some time, I want to spend some time on medical statistics because we are bombarded with them in the last year. if you hear something like cancer strikes 1 in 2 men and 1 in 3 women, does that mean out of a group of 3 women, 1 will get cancer? How do we interpret this? And this is how marketing works. They have like a layman's interpretation of probability that they think is helping, but it's so imprecise. It's aggravating for anybody who knows what this actually means. So usually when you look at statistics, something like this, they believe they're simplifying things, but some things cannot be so simplified without removing the value. So 1 in 3, if you took a random group of 3 women, does it mean 1 will get cancer? Well, no. 1 in 3 women is derived from, and you know, they have all sorts of cancers. Ooh, why can't I type? One sec. One in 3 women is really derived from something like a large population. Let's say, let's make this easy. So it means like 100,000 in 300,000 women. You know, it's really coming from a large population, or usually statistics in science is per 100,000 or per million. Right now, in terms of COVID-19, because they use have a lot of world statistics reporting, they use 1 in a million, or they use per million. So this would turn out to be you would scale this by so what you would do is you wouldn't want this in so you want to rescale this by 100,000. So this would actually say 33,333 per 100,000, which some people will say, oh, that's just the same thing. Well, it's just not. Okay, because it should be considered in a large population. In fact, if you take a small group of 3, let's say you took 3 sisters, this probably wouldn't even apply to them, because cancer is known to be hereditary, and maybe if they have no risk in their family of cancer, then it would be 0 probability. If they have genes that are predisposed to them that make them predisposed to getting cancer, maybe it would be 100% or 3 in 3 women. So looking at a group is not the best way to interpret. The group should be the larger, or the long run, the larger group. Okay, and then in sequential trials, in flipping a coin, for instance, the outcome on the first trial does not influence the outcome on the second trial. These trials are known as independent. So those are just some different uses of probability, and I'm trying to address them here in the notes. Okay. We've talked about independence. Well, what's not independent, and how common is independence? Well, independence is not common. So the example that I gave you, let's do this one, and then I'll talk about that. So let's see here. Consider 4 differently colored M&Ms. Pick one randomly and eat it. If it is blue, then the next M&M you select to eat cannot possibly be blue. So this is an example of sampling without replacement. You eat it, it's gone, and now you're down to 3, and it completely changes the probability of getting the other 3 colors, and the chance of a blue is 0. So these are not independent. The probability of each of the 4 colors is not independent. They change depending on the first selection. Okay. And then I bring this back, tie this back into what you learned about random sampling. In a simple random sample of size n, that sample that you got is independent from any other sample of size n. That's really important for our theory to be able to do what we do with it. So the chance of getting that sample doesn't affect, or this sample, this outcome doesn't affect the chance of getting any other sample of the same size. And we'll talk more about that in the chapters to come, but it's important that you know the independence is across the sample, not just yeah. All right, let me see your comments. No comments. All right. All right, so here we have, I was going to mention something about what I was saying about the hair salon, right? So the hair salon example, I told you about A, hair color, and B, manicure. And if they're independent, what does it mean? And how is that possible? It would mean that if I had my hair colored, the chance that or if a client had their hair colored, the chance that they also have a manicure doesn't change from what it was before you knew the person had their hair colored. Okay, well, is that realistic? Well, depends. Depends. If it's an expensive salon and you are not so wealthy, or you don't want to be or you're more frugal, you don't want to waste money on hair treatments or pampering treatments. So if you had your hair colored, maybe you don't want to spend money on a manicure. In that case, they wouldn't be independent. So even though the example that I used to illustrate independence earlier, even though I used that they were independent, what are the implications, or how could that be? Well, it could be. It could not matter. It wouldn't change the probabilities just because someone had a procedure or a service done. But we could say in general, if having one changed the chance that you want to spend money on the other and changes all the probabilities for the general population, then no, they wouldn't be independent. Okay, so you learned about what probability means. We learned about independence, which is really important. And now I want to get into certain events and deriving probability distributions, and then using the probability distribution to calculate the possibility of outcomes. So what we're doing now is for the sample space. In other words, this is for the we're looking at distributions or the population at large. We're looking at all possible outcomes. Okay. So here's an experiment that we're going to run. This is actually flipping 4 coins. We're going to flip 4 coins, and we're going to define the outcome X. So I'm going to use a symbol similar to, we used the symbol X before, but I'm going to change its meaning. As we go along, I'm going to change it. So for this one, I call X the outcome of flipping 4 coins. Now the outcome could look like this, 4 heads. It could look like this, 3 heads and a tail, and so on. And ultimately it can look like this. So this is not so hard. I could actually think about what are the possibilities here. Well, there's 2 possibilities for the first outcome. There are 2 possibilities for the second outcome. There are 2 possibilities for the third and 2 for the fourth. And if I want to know what are the possible outcomes, it's going to be 16 possible outcomes. Okay. So there's 16 possible outcomes. Now the question is, are they equally likely? Is HHH any more likely to happen than TTTT? So this is the example of flipping 4 coins. The random variable is known as X, or the outcome of flipping 4 coins, and this is the sample space. And my question is, are the outcomes equally likely, or do they have different probabilities? Pablo? You mean no, they should be the same? So they have equal probabilities because because the individual events, the individual flips are independent There are 16 possible outcomes. They're all equally likely. No, you don't have to, this actually, these are, yes, okay, so inherent in here is the concept of long run relative frequency. And I think, head has a 50% chance. So let's see, put that together here. So each one, so if I said head, this is how we would figure it out. And I'll talk more about this after I introduce these topics. But okay, the first thing that's going to happen is a head. What's the chance of a head? In long run relative frequency, the chance of a head is 1/2. What's the chance of a head on the second flip? Well, it doesn't change, it's still 1/2. And on the third flip, and on the fourth flip. So what does that tell me? What do I do with that information? I have to remember what we just learned about independent events. This is the probability of H and H and H and H. Oh, I didn't write and in one of them. Let me do it again because this is important. So the probability of H and H. What am I saying? Hand. Oh, it says and. Okay, so no, I did use it. Okay, sorry. Oh my goodness. Okay, so H and H and H and H. So that would split up into, because of independence, it would split up into this. I think that's messy. I have to fix that. So this is because of independence. I'm just going to write the word independent. Right? So what that means is what I have to do is multiply 1/2 times 1/2 times 1/2 times 1/2. And so what do you get? You get 1/16. So there's 16 possible outcomes, and the probability of this first one is 1/16. Is the probability of the second one 1/16? Head, and tail. So are they all 1/16? Yes, they are. Okay. So because of independence, and because of independence, then they're equally likely. So because they're equally likely and there are 16, you could also say their outcome, the chance of each outcome is 1 in 16. And that could be sorted out by just taking 1 divided by 16, as I mentioned here. Okay. So just a last point. So here you have the this is the description, right, of the phenomena. And then I end off saying the probability distribution. Well, it turns out it doesn't have to be anything fancy. It's just that the probability of each outcome is 1/16. That's the distribution. Now, as if you remember, we referred to random variable as, I'm just sorry, I'm just looking at it. It looks kind of blurry and I don't know why it's blurry. I'm gonna make it bigger. See if that helps. Okay, I'll try and keep it about this size. So if you remember, we used to, when we learned about random variables or variables in the first unit, I mentioned to you that the value should be numbers. And now you could turn these outcomes into numbers. You could say let h be 0, and then h would become 0, 0, 0, 0, or just 0, right? And t could become 1 because it's 0, 0, 0, and then 1 because t would be 1, and so on. So you could translate all these outcomes into zeros and ones. Anyway, so that's my first example. The second example uses the phenomena described in the first, flipping 4 coins, but I'm interested in a different outcome, a different variable. The variable is going to be defined now using the same symbol x as the number of tails in 4 flips of a coin. So what I'm doing here is taking the outcomes and I'm grouping them into 0 tails, 1 tail, 2 tails, 3 tails, and 4 tails. And you see here the possible outcomes. Now we know for all these possible outcomes we have their probability, so I could now group them, and I refer to these as singular outcomes and these as compound, just to help you understand within, if I call this event 2, right, or 2 tails, there are outcomes with singular outcomes within this compound event. Okay, so it's just to illustrate some of the terminology. So now what is the chance of getting a 0? So we could write, now we can write probability of 0, sorry, I could write it, since I've called x the number of tails in 4 flips, I could say what's the chance that x equals 0? Or what's the chance that x equals 1? Now this looks familiar. However, we are now working with a discrete distribution the values are whole numbers, and not continuous, right? Let's see. Actually, we're going to call this, it's not discrete. We would call this is like a categorical. Let's see. It's discrete, not continuous. That's true. And yeah, we'll just leave it like that. Discrete. So this looks different. So now, because it's discrete, not continuous, there is actually a probability of a certain outcome. And there's only 5 outcomes. Either x is 0, x is 1, x is 2, x is 3, or x is 4. Now, what is the probability of each? Right, so Pablo has given us the first one. Each one of this are 1 in 16, right? So each of these are 1 in 16, and we can use that fact and our intuition about probability to calculate the probability of each. Now here, this one is just 1/16. This one, there's 4 with 1 in 16. Can I just add them? What is the theory that we're using here? We're saying probability of H, 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 T, or H, H, T, H, or H, T, H, H, or T, H, H, H. How do I calculate then the probability x equals 1? This is the same as this, or this, or this, or these. These are all together under the banner x equals 1. So I just add them, right? Because these are disjoint events. It's either one of these happens, not 2 at the same time. So we use the idea of disjoint events and their probability to do this. So the probability x equals 1 so you should have an intuition for making these calculations, but I'm trying to tell you why you're allowed to do that. So x equals 1 would just be 4 out of 16, and using the same logic, x equals 2 would be 6 out of 16, and x equals 3 is 4 out of 16, and x equals 4 is 1 out of 16. And that's it. So what we've done is we've used the probability rules or properties that we've discussed so far in our overview, and we've derived a probability distribution. It's a distribution because it demonstrates all the possible outcomes, 0, 1, 2, 3, and 4, and their chance of occurring. And that's a distribution. Oh, so take a screenshot if you want. I'm going to move to the next slide page. So we can fill in this table here. We already did this, right? Let's just fill this in here. So this was 116. This is 416. And what you would do is set up this table demonstrating. So this table is analogous to the Z table that you were using in the normal distribution with thousands of values in it, thousands, hundreds of values in it, but there's only 5 here. 0, 1, 2, 3, and 4. And like any distribution, the total possible outcomes, their probabilities must sum to 1. Okay, so this has to be the case. So that's true. Now, we've got this. This is a simple example. We're going to answer questions regarding this distribution as an illustration, and then we're going to use this similar, this technique for other problems, maybe more complex problems. So the idea is I illustrate using a very simple example, and then later when we get to Unit 5, you'll see I'll come back to this and demonstrate there's a pattern that we can exploit for more complex problems that are similar. Okay, so what are the other, what kinds of things can I do with this? So this distribution, this shows me the possible outcomes of flipping 4 coins. There's still randomness, right? And these, the chance of getting 0 tails is 1 in 16, and the chance of getting 4 tails of 1 is 1 in 16. So these, it's like symmetric. There's like a pattern here. Getting 1 or getting 3 has the same, 4/16 and then 6/16. All right, so what if I use this to answer certain questions? So just to practice interpreting problems. Now I'm thinking, let's take 5 minutes break. I want to try and see if I can change to make this less blurry. Let's take a 5-minute break and we'll talk about this in a bit. All right, I'm back. It didn't work. What I was trying to do. Can you hear me? Okay, let's continue with this. All right, so let's use the probability distribution to answer questions. What's the chance if you flip 4 coins of seeing at least 2 tails? So at least 2 tails would be, well, here are the possible outcomes. I've listed 0, 1, 2, 3, 4. At least 2 tails would be 2, 3, or 4. So if you ever get confused with these problems, it just seems like the human brain works well when you think about money, okay? So numbers were developed for exchange in the general public. I think it affected our brains and evolution. So we're really good when I think about money. So this is not about money, but I could say, well, at least $2 to help myself realize it's 2, 3, and 4. Okay, so at least 2 tails. I could write it like this as well. I could write it in words. And then I identify the probabilities associated with that and I sum them. I sum them because these are disjoint events. Probability of x equals 2 or x equals 3 or x equals 4. So because they're disjoint, it's only one or the other, I can just add those. And that is 11/16. If you don't like fractions, I've also included the decimal values, but you should practice with both, okay? You should practice with both. So in that spirit, what's 11/16? What about the other ones? So less than 3 tails would look like this. We write it like that. So it only includes 0 tails, 1 tail, or 2 tail. again, you get 11/16 or this. And then lastly, less than 1 tail or more than 3 tails, that you could write like this, x less than 1 or x greater than 3. So that's just going to be x equals 0 plus x equals 4 with the same logic as before. It's just these two. And that's 2/16. Now I don't bother simplifying the fraction or anything. I just write it 2/16, and then you can write it as a decimal. Okay, so what have we done? We've discussed an event, which is any collection of results or outcomes of a procedure. A simple event, that's an outcome or an event that cannot be further broken down into simpler components. A compound event is combining 2 or more simple events. So if you've come across this terminology, that's all it's talking about. And then the sample space, which is consisting of all the possible simple events. So the important thing, we will import probability theory into statistics to be able to answer questions about a population from analyzing the estimates of its parameters and vice versa. That's where we're heading with this. Okay, so let's look at probability rules. We already learned them, or we already discussed them, but let's address them in a systematic way, one at a time. So the probability rule number 1 is the probability of any event is between 0 and 1. We can write it as, any event A is between 0 and 1, any other event B is between 0 and 1 inclusive. Rule number 2, all possible outcomes together must have probability 1. We write that like this. Sometimes I use PR or just P. They're the same thing. Don't let that confuse you. The third rule is the complement rule. 2 events are complementary if only one of these events can occur at any given time. We can write A complement or not A or A with a C. So superscript C. If 2 events are complementary, these 2 events are the only events possible. Thus, complementary events are a special set of disjoint events. So we've already talked about that, and I provide some examples here you can have a look at here and here. Rule number 4 for disjoint events. 2 events are disjoint if one of these 2 events occurs at any time. They have no common outcomes, and you can have this outer space occur as well. So this is the space of, or the event not A or B out here. So if A and B are disjoint, we have a special rule for the union of events. If A and B are disjoint, then we just have to add their probabilities to find out the probability of either of them occurring. So those are the first 4 rules that we've already learned. Now we're going to apply them. We already have applied them, but here's another example for you to try. So I'll give you a few minutes to work on that. I'll give you 2 minutes. That's all you need. Okay, I'm back. How'd it go? How did you approach this? So I'll create my sample space and I'll let A be the event the doctor is in his office at 48 probability. And B is that he's in the hospital, and they're assumed here mutually exclusive. Now, I'm not going to draw this to scale exactly. This is just a sketch, but that's the idea. So what is the probability the doctor is not in the hospital at 9:30? In other words, B, not B. Probability of not B. So that's 1 minus the probability of B, which is 1 minus 0.27, which is 0.73, or 73%. What is the probability the doctor is either in his office or in the hospital? So that's A or B. They are mutually exclusive, assumed here. So this is why in the test you need to write your answers on separate pages so I can see what your assumptions, excuse me, what your assumptions were in the incident, that they are, that you interpret it differently than I did, okay? So in this case, I just add these two together because I've assumed the disjoint. So you get 75%, that's right. And then finally, if the doctor didn't go to his office or the hospital, then he went home. So out here is home. What is the chance he's at home? It's 1 minus office or hospital, which is 25%. Okay? So this is very easy exercise, but that's how you would tackle them. Okay? You draw it and understand the different events, and it's very easy to calculate the probability. So those are the first 4 rules. Then comes our discussion. We had our discussion with an overview of all the different ways you could see 2 events. There's one more diagram that's possible that I do discuss in the notes. And I didn't mention it, but these are called Venn diagrams. These are Venn diagrams. I'm surprised I didn't mention it. Or maybe at the beginning I did of the notes. Okay. These are Venn diagrams. And these are something you're introduced to in elementary school, or you should have been. Okay, but obviously not as complex as we've done this, but the principle of events and illustrating them in a sample space. Okay, so then I go into the discussion of independence, and I talk about it here, and I have a last example before I proceed with the final 2 rules. So let me bring all these concepts together, independence, long-run relative frequency, with this example. First, let me say, in words, if an event A occurs 30% of the time, and of those times, event B also occurs, use a multiplication for the of. Okay, so how do we do that? So this is the idea of independence. Because event B occurring within A having occurred should remain 40% because of independence. So that's another way of saying so the conditional probability of B given A is just B if A and B are independent. Okay, so let's go to our salon example and I'll give you more details. Let's say there are 10,000 women in this population of customers. A is the event of a manicure and B is the event of hair coloring. So we surveyed a large population and determined that 30% of the time customers will have a manicure and 40% of the time they'll have a hair color. Oh, I did it backwards here. Well, than what I was describing, but that's fine. That's what I did, right? 0.3. Okay, so that's going to be the story. In case 3, what I'm talking about is actually case 4. This is like case 4. In case 4, you are told that you should assume A and B are independent. And then you can answer a question, how many women have both a hair color and a manicure? So you want to figure out what's the probability of A and B. We know how to do this. We know we just multiply because of independence. And because of the interpretation I've made here in words, we just multiply them. But I want to illustrate, and this sometimes helps people to understand the long run relative frequency, how we can use it. So let's say it's 10,000 is enough to exhibit the long run relative frequency. So 30% of 10,000 is actually 3,000 women that had a manicure. Because of independence, 40% of this subset, not just 40% of the 1,000, but 40% of this group of 3,000 also had a hair color. So all I have to do is take the 3,000 and times by 0.4. So now I get the result that 1,200 women had both services. I could do this the other way too. I could say, well, let's look at the hair coloring first. So 40% of 10,000 had hair colors. That means 4,000 women have their hair colored. Because of independence, 30% of this subset also had a manicure. So 30% of that is also 1,200. So it doesn't matter which way I do it. The big thing was assuming, well, there's a few assumptions here. Well, let's say 10,000 is the long run. Okay, so it's enough to see the long run relative frequency. To be able to make those calculations. Also, independence. If you calculated A times B at the outset, you would have had 0.12. But doing it this way, I demonstrate to you what exactly we mean. I think it's a good example. So independence is a special characteristic. It's not exactly common. However, in statistics, and in particular in introductory statistics, it's used a lot. But just because it's used a lot for the theory to simplify calculations, and it's a common assumption in statistics, doesn't mean it's common in reality, okay? You got to be careful about your assumptions always. Economics, statistics, finance, business, always know your assumptions. So as I said, in this example, I gave you the information of independence. That's why you could use it. Okay. So here we have, and I've done, whenever I mention in my notes tiny URL, it's because I have a video on this. So you can rewatch the edited videos. In my edited videos, I don't make mistakes. But you have to hear the cookie because I made those videos a while ago. And I just didn't have a way of drowning out the cookie when I made my videos. Okay, so here is another example. What I want you to do, I'm going to ask you to take 5 minutes to depict compound event A, compound event B in this sample space. And then we're going to calculate just like we did before, A or B, A and B, and not A or B. Okay, so draw it and see if you can answer those questions. So I'm going to leave you with this. You should have the notes in front of you, but if you don't, here, I'll give you this here. I really don't know why my screen appears to be blurry. I have to sort that out after this class. Are you finding that as well? It's blurry? Bothering me. Readable is not good enough. I want it to not be blurry. It's funny. Just read your comment. Okay, let's see. I don't know why it's like that. The other videos weren't like that. But okay. So what did you draw? Event A is observing two tails in 4 flips of a coin. So that is down. Actually, you know what I'll do is I'll bring them. So this is A. And B is 3 simple events. It's 0 tails, oops, 1 tail, and 2 tails. So you can see them. So B has more events in it than A, so it's going to be more likely. So how do I draw this? It's important to note the relationship between A and B. A is completely inside of B, and that's what makes me draw this like this. Oops, I did it wrong. I did it backwards. A is completely inside of B. So that is the depiction. So that's like the 5th relationship that you can expect to see in this class between 2 events. This is not such a great idea, right? I want to make these. Anyway, there you go. So A's probability, you can calculate, is 6/16. B's probability is 11/16. And now I want to go into, so I put them here. And now I want to understand what is A or B. A and B are not A or B. So A or B means either being an A or B, but A is inside of B, so A doesn't add anything extra. It turns out the probability of A or B is just the probability of B, which is 11/16. And the probability of A and B, where do they intersect? They intersect just at A. So it turns out that this is just A. And then the outside space, not A or B, is just 1 minus the probability of B, because A or B is B. Well, let me write that. A or B equals 1 minus probability of B. Okay? So A or B is not A plus B in this case. In fact, A plus B would make you go over 100%, right? Because it's 6/16, 11/16 makes 17/16. That's too much. So you really need to know the relationship of your variables before you can calculate probabilities. Okay, so that's like the fifth sort of relationship you can expect to see. Between the variables. So I'll just make a point just to say okay, you can't add them because they're not disjoint. They're actually completely contained. One is contained in the other. Okay, so what's next? All right, so here we have, what we have here are probability distributions of two variables at a time. So this is called a joint probability distribution. So you have, this is a little bit different than we saw before. You have one variable's outcomes here and another one here. The other thing to point out is these are two discrete. So I stick with discrete distributions. And discrete variables because otherwise, if we go into continuous variables to do this, we need to use calculus and particularly yeah, well, it's more complex in terms of the mathematics, but it's the same idea. So this is good enough to make the points I'm making. So verify that this is a legitimate assignment of probabilities to these outcomes. How do we do that? Well, what's legitimate is that they all have to total 1. So you have to check. If you sum these together, they should total 1. Or 100%. Now I ask you for specific outcomes. What is the probability that a worker is female? So that would translate into the probability of women. And you would get that by adding together the following. So let me explain to you what these are each are. So probability of woman or women and A would be this event here. Okay, so each of the cells is this and that. Probably should say female. Anyway, B. I think you get the point. So I have to sum across. So if you sum across, this is known as the marginal probability. You should get 0.4. And since the total must be 1, this one has to be 0.6, right? So the answer here is 0.4, 40% chance of a female employed, smaller than males. What is the probability that a worker is not engaged in F? Well, F would be here, so these are other marginal probabilities here. And this one here would be probability of F. If I sum those two, it's 0.04. For D or E, I have to sum all of these. So let's just put them all here. 0.04, 0.14, 0.14, 0.17, 0.31, and 0.2. All I need is, for the next one, D or E. So the probability of D or E is the sum. Okay, so this is prepared so they are mutually exclusive. That's how it's been prepared above. So you just sum those and you get 0.18. So you've answered. So this is another way to see the distribution as a joint probability distribution. So two events at a time and their interrelationship. And each of these cells is AND. So, oops. So as I described here, the cell is one. Oh, I did the wrong one, did I? Women? Women, yeah, no, this one. 0.08, woman in A, woman in B, woman in C, etc. Oh, I didn't do the not, right. So finishing number C, F was 0.04, but they're asking for not F. Right, thank you. So it's 1 minus F, which is 0.96. Omar, thank you. Okay, so that's how we work with that kind of a distribution. The joint probability distribution. And finally, that brings us to a question. Oh, did I talk about rule number 4? Yeah, I did do rule number 4. Okay. So the question is, are occupation A and being female, are those independent events? So what would that mean? That would mean that if they were independent, it means that observing someone is an occupation A. So let's say they were dressed up. We saw someone dressed up in a in scrubs in a nurse's uniform. We knew they were a nurse. What's the chance of them being female? Should that change is really the question. Should it change if I know? Should the chance of being female and known to be in occupation A be different from the chance of being female in general? If there's no difference, then they would be independent for occupation A. If there is a difference, then they're not independent. So we can check. We can check to see if that's the case. How do we check? So here I have probability of being a, let me write it in the order I was already. Woman, well, let's do it here. Okay, so A and female or woman. The chance of being both in occupation A and a woman is given in the table, 0.08. The chance of being in A, being in occupation A, is 0.2, and the chance of being a woman is 0.4. So all we need to do is check if there's any difference between A and woman and A times woman. Now we have no other information. We just have the numbers, so we can't do any other, we don't need to do any other investigation. We can just check this. So what's the chance of being A and woman? We already have that. That's 0.08. And what's the chance of A times woman? Well, A is 0.2 and woman is 0.4. And look at that. They're the same. It doesn't have to be the same, but in this case it was. So how is this a proof? What do I do? So I say, if independent, the left-hand side, that's what that stands for, is equal to the right-hand side. So this should equal this. Since this is true, They are independent. It means it's an occupation where seeing the gender doesn't influence whether the person is in that occupation, or seeing the occupation doesn't influence whether they're a certain gender. Any questions? You can try this for other events to see if it's true. Is it always true? What about are male indeed independent? The probability of male we already found was 0.6, and the probability of D is 0.14. If you multiply them, do you get the same as this value here? No, you don't. Okay, and you can write that down just like I did below for women in occupation A. So that's an occupation where knowing the occupation will change the chance that it's a male. So let me elaborate a bit just so you see what I'm talking about. So probability of D and male should equal probability of D times the probability of male given D. So what I'm saying is, we know this is 0.14, but we don't know this. The male given D. So we know the occupation. What's the chance of being male? We know it's not going to be 0.6. The table tells us. And 0.14 times 0.6 is not 0.13. So since they're not equal, it's not independent. Okay, so that could be any occupation where the probability of being male is different from the general population. In fact, since it's 0.13, Because if you multiply this, as though it was that, it's smaller. So the chance of being male has to be greater. It must be more than 0.6 to get a higher number. Okay, so this could be which occupation are you likely to see more men, maybe in physics, or let's see, I don't know if it's an occupation class. Oh, construction, let's say construction. There's some women in there, but there's by no means the same ratio as the general working population. So just to recap, if you didn't follow what the heck I was saying, if we were to multiply them as though they were independent, we get the value, this value here. But that's not the value in the table. The value in the table is higher. So the only thing that can make it higher is the unknown multiplying by a higher number of male given D. So male given D must be more than 60%. So if you didn't get that, I encourage you to review that in the video, and let me finish the class with the last two rules, and I'll leave you to practice the homework and exercises I've given you that are quite basic. Rule number 5, the multiplication rule for independent events. If you know A and B are independent, then the probability of A and B is just their multiple. Where in more general terms, we write that A and B is not just A times B, it's A times the probability, the conditional probability of B given that you see A. Only if they're independent is it the case that it doesn't matter that we saw the event A. The subset A, the event of, in the subset, the chance of seeing B is the same as in the general population. It doesn't change. So in summary, if you are asked to calculate the probability of A or B and they're disjoint, you just add. Just to simplify things, I put the summary in. So you add for disjoint events, but when you have independent events, you multiply. So independence and disjointness are different concepts used for different purposes. So to find the probability of A and B, you multiply probabilities if they're independent. To find the probability of A or B, you add probabilities if they're disjoint. And then I have a bunch of exercises for you to try. Exercise. And then this is a review of probability models. And I will do this next class, so you should read ahead. So I'm going to talk about the models we'll see in the class and hint at other kinds of models. And then this is really important. Review this practice assignment. The solutions are all here, and we'll talk about one of those problems that I like to show. And so So this is like a lot of stuff here. So review that, and we'll start, this will be the focus. So hopefully we'll spend no more than an hour on that, and then I can work on conditional probabilities and means and variance rules. So you should read through all of this, and I will make it much more clear in next class. You can even try this quiz. I give given the solutions to almost everything, except for a few exceptions that I'll leave for illustration in class next week. So that's it. So you work with Unit 4. It's all pretty... You're capable of doing all of it. You can do all of this on your own, but I'll help you out next week in the review. Okay, so work through this and send me any problems you have so that I can either illustrate them in an office hour session. I'll just say also, so next class we're going to meet, and then the following week I'll do review exercises and things. To study, you should be practicing the old midterms for RLS. If you've run out of exercises to practice. But then the final exams for probability. So start working into the final exams once you get through these notes to practice probability. So hopefully once we finish that test, we're going to be on to the last 2 units. And once we're finished the units, I will give you a 3rd test, and then the final exam will include everything, okay? And the final exam, I will talk about it as we approach it, what it's going to look like. But I did leave information in the final exam module online where it demonstrates the breakdown of the test, okay? What chapters are more important, or the emphasis, where the emphasis is. Any questions? So with that, I'm going to sign off. Unless you have some questions, I'll stay on here. And hopefully if you're watching this later after the class, I hope it's helpful. Let me know if you have any questions. Okay, so take care. So maybe I think after the second test, we'll have a meeting together. I don't really want to use the time before the test. So the class after the second test, we'll have a meeting in Teams and see if you guys feel better being able to communicate verbally. What I'll do is I will broadcast the Teams meeting on YouTube so that gets saved for later use, and it appears in my playlist for you guys to view at your leisure. Can I go back to D with 0.18 answer? What did I do wrong? D. Did I do something wrong? Oh, I probably added something wrong, right? Oh, 0.1 D and 0. Yeah, I probably added them wrong. I didn't finish or something. So this one is D is 0.14. I don't know what I was doing. And E is 0.14. And it's 0.28, not 18. Sorry. Thank you for correcting me. I wish you told me sooner, but I hope everyone got that.